Hi, welcome to week 2. So, towards the end of last week, you were introduced to functions and function notation. And this week, we're going to continue looking at functions, but we're going to focus specifically on the domain and the range of a function, what it means, and how we find it. And then also, you'll take a look at how to calculate the average rate of change between 2 points of a function to see how that function behaves or changes over a specific interval. So let's recall what a function is. So a function has three main parts. There's an input value, a mathematical rule that tells you what to do with that input value, and then once you use that math rule to evaluate that input value, it gives us a corresponding output value. So here I have an example of a function, y equals 2x plus 5. So let's recall that x is our input value. And I can evaluate this function using different x values, and it's going to give me corresponding y values, which are our output values. So when we're interested in talking about the domain and the range of a function, let's call y f of x. So let's let y be f of x. So we're naming that function f of x. The domain of f of x is the set of all the possible input values, so all the x values that will yield an output value. And so then all the corresponding output values of this function it becomes the range. So the range is just the set of all the y values that you get for each individual x value that you put into the equation or the function. So let's say, for example, let x be 4. Then we can evaluate the function when x is 4, so f of 4. That gives us 2 times 4 plus 5, which is 4 times 2 is 8, and 8 plus 5 gives us 13. Okay, so 4 is a part of the domain of the function f of x, and 13 then becomes a part of the range, okay, of the function f of x. Now, 4 and 13 are just one of the values in the set of the domain, the set for the range. There are many other values. So sometimes it's easier for us to determine what the domain and the range of a function is by considering its graph. So let's take a look at the next slide. So here I have a graph of the function y equals 2x plus 5. And again, sometimes a graph makes it easier for us to see the domain and the range. So if we're talking about the domain and the range of this function, again, recall that the domain is the set of all the x values. So all the x values that make this function exist, it consists of all the points. So I'm just putting a couple here, but you can imagine that this line, y equals 2x plus 5, is made up of an infinite number of points, and every point has a coordinate, some x comma y. So every single x value that makes up this line, right, that makes up the domain for the function. So if we think about this line, as it increases on the right here, notice that it contains x values from 0 all the way to positive infinity. And then if we take a look at the function on the left here, we see that the points that make up that line there have x values that go from 0 to negative infinity. So this tells us that the domain is all the x values from negative infinity up to positive infinity, or you can just say that the domain consists all the real numbers, and that's the notation we use to represent all the real numbers, all the negative numbers, positive numbers, whole numbers, decimals, etc. And then now the range is a set of all the y coordinates that make up this function. So I'll use red here. If we think about the y values, notice that the y coordinate of every single point on this line, right, as the line increases, we have y values that are 0 or greater. And then we also have y values, if we take a look at the left side of the function here, that are negative. So the y values consist of all the real numbers from positive infinity to negative infinity. So we can write that using set notation as y. The range is all the negative numbers all the way up to the positive numbers, or again, the set of real numbers. Okay, so here is another example of how to find the domain and range of a function where there's some context. So, lidocaine is a drug that's used to treat irregular heartbeats, and we can actually measure the amount of the drug that's left in a patient's bloodstream. We'll call that A, so the amount of drug left over time, which we're calling T. So, let's define T as time measured in minutes after the lidocaine's been injected. And so we can actually call this function A using function notation. I'll call it A of T. So if I want to know what is the domain of this function, the domain represents all the possible t values that make sense for this problem. So if t represents the time in minutes after the injection, then it makes sense to only look at positive time because it doesn't really make sense to talk about negative time. So the domain that would make sense for this function would be all the t values from 0 minutes all the way out. And we can take a look at what's left in a patient's bloodstream over a very long period of time, so all the way out to positive infinity. So we would write the domain as t greater than or equal to 0. Now, when we talk about the range represents all the corresponding output values that make sense for this particular function. So since the range is the amount of lidocaine in the bloodstream measured in milligrams, then we would expect that the range would only have positive values, okay? 0, and then it doesn't go all the way up to positive infinity, but it hits the maximum amount. So those of you who are nursing or registered nurses in this program, hopefully you probably know that when medication is being given to a patient, it spikes. Initially, it spikes, okay, as the level is most active in the bloodstream. But then over time, if we don't give the patient another shot or another dose, we would expect that the drug is going to eventually evaporate or get eliminated from the bloodstream. So that's why it makes sense for us to talk about the range going from 0 milligrams up to the maximum amount. So we know that eventually the lidocaine is going to leave the bloodstream, leaving 0 amounts left in the bloodstream. It's never going to, dip past 0 and get into the negative numbers. And so again, sometimes it's easier for us to take a look at the domain and the range of a function by looking at the graph. So in the next slide, I'll show you a graph of this lidocaine. So sometimes it's easier for us to find the domain and the range of a function when we have a graph of the function. So here is a graph of that function A of t, that the amount of lidocaine in a patient's bloodstream. So the x-axis here, these numbers down here, represent time measured in minutes, okay? And we can see that the amount of lidocaine in a patient's bloodstream, I'll use green here, at 0 minutes, okay, there's obviously no drug in the bloodstream, but initially the amount of lidocaine, it spikes, it goes up, and then it hits a maximum point, which is where the drug is most effective. And then over time, we can see that as time goes on, the amount of lidocaine starts to decrease because it's slowly being eliminated from the body, but it's going to approach 0, never passing 0, because it doesn't make sense to have negative amount of lidocaine in your bloodstream. So with that said, because it doesn't make sense to have negative amount of lidocaine in your bloodstream, I'm going to use bright red here, you can see that this part of the function down here represents negative values of the amount of lidocaine in someone's bloodstream. And since that doesn't make sense, we don't want to take a look at this part of the function. So this part of the function is made up of negative t values. And so that's why we would say that the domain, we're not going to look at negative time. The domain would only make sense for us to consider positive minutes, starting at 0 and all the way up to so we would say t is greater than or equal to 0, okay, all the way up to positive infinity here. Even though it doesn't make sense for us to, take a look at the amount of drug in someone's body over an infinite number of time, in theory, we're saying that over a long period of time, all the t values that make sense for this problem, we could use values as far out as, 5,000 minutes if we wanted to. Okay, and then the range is all the corresponding y values or output values. So in this problem again, hopefully you can see that the range goes from, and I'll use blue here, the range goes from 0 up to the maximum amount. So that's the range, and that makes up all the y values for this function. So the range here would be all the y values or the a of t values that are greater than 0, it could be equal to 0, but less than that maximum amount, and that maximum amount is 25.6 milligrams. Okay, the other thing that you're going to focus on this week is how to calculate the average rate of change. So recall that the rate of change between 2 points, it lets us know if the function's increasing or decreasing over that interval. And if we actually do the mathematical calculation and get a numerical value for the rate of change, the number that we get tells us also how fast or how slow that increase or decreases over that interval. So again, let's use the graph of the lidocaine function just to kind of talk about how we can visualize rates of change of a function. So here I've got a graph of that lidocaine function again, and a couple of things that I want to talk about. So here, anytime you have a graph of a function, it actually makes it easier for us to see how it changes over time. So here, the lidocaine function, we can see that over time, the function increases, hits a maximum amount of lidocaine in the bloodstream, and then it starts to decrease. So there are certain intervals where the function's increasing, and then there are certain intervals where we can see that the function's decreasing. So I'll use green here to highlight where the function is increasing. So here we can see that when t is 0, so between 0 and this point right here is when t is 24.5 minutes, we see that the function is increasing between over that interval. And then I'll use red here. We can see that after t equals 24.5 minutes, the function starts to decrease. So the function decreases after 24.5 minutes. And then also we can say that the function hits a maximum right at 24.5 minutes. Now, when it comes to talking about the rate of change, let me erase some of this right here. Okay, hopefully you can see, and I'll use a different color here. I'll use bright green again. If we take a look at where the function's increasing, right, I have 2 points here. I'll call this point A and point B. When I connect point A and point B, I hope that you can see that the rate of increase is really fast because the slope of that line is pretty steep. And now I'm going to use blue. If we take a look at point B, and I'll call this point C and connect it with a line, you'll see that even though the function is increasing between B and C, it's increasing at a slower rate. So it's still increasing, but the rate at which it increases is slowing down. So the average rate of change between point B and point C is going to be a smaller number than the average rate of change between point A and point B. But any average rate of change that we calculate over the interval between t equals 0 and t equals 24.5, the average rate of change is always going to be positive because the function is increasing over that interval. Now, after the point C, I'll use red here again, we can see that the function is decreasing. So if I were to pick any 2 points where the function is decreasing, let's say point C and point D, the average rate of change is going to be negative because here, if I were to connect those 2 points of the line, we get a negative slope, and then we can also see that it's slowing down. Now, if I choose one more point, like point E, hopefully you can see that the function is decreasing a lot faster between point C and point D versus point D and point E. So between point D and point E, the function is still decreasing, but the rate at which it decreases is slower. So the average rate of change between point D and E is going to be smaller than the average rate of change between point C and D. But anywhere where the function is decreasing, that average rate of change is going to be negative. So these are just different ways for us to visualize rates of change and see how the average rate of change tells us how the function changes over time.